Hello, welcome to video 53 in the lecture Advanced Mathematic Modeling. In the last video we have looked a lot at fractals. These were objects from nature that had all kind of information built in at different scales. So they were self-similar, so if we magnified the object, we found the same information again. And then we saw that this led to all kind of weird geometric behavior. For example, in a coastline, when we zoom into the geometry of a coastline, we find more and more structures which are hidden at smaller scales, and thereby the length of the coastline was increasing with scale, and so basically it's not defined if we don't give a characteristic scale. And in particular, if we try to find out the total length of the coastline, it diverged. So the length of the coastline was infinite. And then we had many other examples of fractals, or I showed you or told you that this other examples are also fractal. But we can also, and this is what we're going to do in this video now, look at fractals from a mathematic point of view, because in nature, I mean, the self-similarity can always be an approximation, and as we said, only be valid within certain range of scales. But in mathematics, we are free to define pure fractals which are self-similar to until the last iteration, until infinite iterations. And this is the topic of this deterministic fractals. And I think the best way to do it, to introduce this is by examples. So let's look at the Koch curve. And this is an object that we generate by iterations. Let's write it like this. It's a fractal generated by iterations. And so there's many variants of all these deterministic fractals, and they all start with a starting object. So in the 0th iteration, and the starting object is just a small line segment of length 1. So that's the 0th iteration of this object. And now what we're going to do, so it has length 1. And now we go to the next iteration. And so what we're going to do, we take the object. So that was this object. It's just written a bit smaller. Then we make another copy of this object, another copy, and another copy. So we have 4 copies of this object. And they're arranged in this geometry, so that we change the angle a little bit between the second and third of these copies of the object. So this was the 0th generation or iteration, and this here is the 1st iteration. And now we see how do we continue. Now we want to go to the 2nd iteration. And now what we do, we take every part of this object and replace every part. We do the same procedure again for every part of the object. So in the 2nd iteration, we take the first segment and we replace it by this. Then we take this segment. Now we do again the same thing, but with this changed angle. Now we take this object, and then we take the last object. So this would be the 2nd iteration. So we have the 2, and now we can see what's happening if we go to the 3rd iteration. And then we obtain an object like this. So that's the third iteration, and so on and so forth. And this would be our model for the coastline of England. Model for the coastline. So that we say, depending on the scale that we're looking, let's say, for example, that's the coastline. If we now look at this coastline at a larger scale, and the small irregularities are not there, then we see this. And if we look at even larger scale, we suddenly see this. And if we even look at a larger scale, we see just, it's going from left to right, we see only this. And now we can continue this. And the Koch curve is the limes when the iteration n goes to infinity of this object here. Object n. Yeah. So if we just continue this infinite times. So now let's look at the length. So what is the length of this? So let's take the length of at the 0th iteration, then the length of the object is exactly 1. So what is the length in the first iteration? So what did we do in this iteration? So we have 4 copies of the old object, but yeah, actually the first length should have been here exactly like this. So what we do, we take, maybe you see it better here between the first and the second, we take every length that we have, we divide it by 3, so that we have smaller ones here. So actually, so yeah, I have to make it correct. The first length should have been larger. I just didn't do it for sake of space, but I should have done it. So the first length is this, and this is exactly the same length to the beginning and the end of the next iteration. So this stays always the same. But this means then if we now make the iteration, we first have to scale the object by a third, and then we make 4 copies. That means the length of the first iteration is 4 over 3, 4/3. Yeah. And then what's the length in the second iteration? The length in the second iteration, now we take every straight line here is again divided by 3, and then we make 4 copies. So then we have 4 over 3 to 2. And then we see the length of the nth iteration is 4 over 3 to power n. And then you see we have exactly the same behavior as in the coastline of England. If we increase reduce the scale, so look at this with the smaller, higher resolution, the length is increasing. Yeah. And now if you take the length of the Koch curve, the limit of this to infinite is not defined. So the Koch curve is a geometric object which has infinite length. And then we can now see how can we calculate the fractal dimension of the Koch curve. So how do we calculate this? So first we need to see what is the scale, and then we see the scale is the length of all these objects. So the scale here, epsilon 1 is a third, and here epsilon 2 is a ninth, and so on. So the scales, epsilon n, and then we have epsilon n is 1 over 3 to power n. So these are the scales. And if we look at the object at such a scale, we find here the length of the object. And now remember how we calculated the fractal dimension. So the fractal dimension was defined as the limes if we go to smaller and smaller scales, and then we needed the log of the number of objects that we have divided by the logarithm of 1 over the scale. And now if we go to the Koch curve, so we have the number of objects and the scales at different iterations. So we have to calculate the limits when the iteration goes to infinite of logarithm of the number of objects depending on our iteration divided by the logarithm of 1 over this epsilon n. And so what we still need is this n here. So how many objects we need to make a coverage. And you see here in this case here, if we make a coverage, in this scale we need 4 scales to cover this. So we see here 4. And here, if you look here, we have 4 squared. And here 4 to power 3. So n there equals 4 to power n. So number of objects that we need. And then we can plug this in. So we need now the limes n goes to infinity of the logarithm of 4 to power n, this is this here, divided by the logarithm, now 1 over epsilon. Epsilon is 1 over 3 to power n, and 1 over epsilon is 3 to power n, so we have here 3 to power n. And now you see, if you take the logarithm of something to power n, so we see we have here n logarithm of 4 divided by n logarithm of 3, and the n's cancel. So we see we don't even need to take the limes n goes to infinite, because this increase in the number of objects we need to cover a certain scale epsilon is directly the same, independent of n. It's always this constant, and that's the fractal dimension. So log 4 divided by log 3, and so this is about 1.261, and that's the fractal dimension. And actually that's a value which is not so far from the measured fractal dimension of the coastline of England. And so this was now the generation of the Koch curve. In a similar way, we now can construct other fractal objects. I just want to give some examples. In the exercises you will see some more. Take for example the Cantor set. So the Cantor set goes back to mathematician Cantor. It was long known as in mathematics before Richardson or Feigenbaum, but maybe not regarded as a fractal as before. And so how does the iteration goes in this case? So we start again with the same building block, this here. Then we divide this again in thirds, but now we take only 2 objects and we leave the middle one empty. Yeah. So instead of plugging here these 2 lines so that we have a continuous curve, now we get 2 smaller line segments. Yeah? So we get a length, this is reduced. Now if we continue this, Then we have here smaller lines, larger interval, and smaller lines, and so on and so forth. Yeah? So so we get into more and more a set of more and more smaller objects here. And so we see that actually goes to something which has a dimension then probably smaller than 1, because this goes to a dust rather than to a thick curve. So let's try to prove this. So let's calculate the length here. L0 is again 1. Now if we take L1, this here, this has now the length of 2/3. Right, so in comparison to the Koch curve, which has had a length of 4/3, so the length of this was increased. In the Cantor set, we keep only 2 parts of this divided object, so the length is reduced to 2/3. And then L2 is 2/3 to power 2. And then we see that Ln goes to 2/3 to power n. So you see here the length of the Cantor set goes to 0 if we iterate this to infinitum. Infinitum. And so the scale, so what's the number of objects? Then n in this case is 2 to power n. The scales epsilon n is again 1/3 to power of n. And then in the similar calculation as before, we obtain the fractal dimension. Yeah? That's everything the same, but only we have here 2 to power n. And then we have ln2 over ln3. So that's something like 0.63. And that's the fractal dimension in the Cantor set, which is smaller than 1. Yeah? So we have a dust. And let's make another example. Sierpinski. Gasket. And I again make something very similar. I start again with here a line. So we have here always fractals which are based that we divide something into 3. And in this case, now we start with a 2-dimensional object with this triangle. And now we do this, that I divide this object that only 3 smaller triangles remain. So that's already the first iteration. And in the second iteration, we take again every of the 3 remaining triangles and divide this again in smaller ones. And then we keep the remaining areas, and so on and so forth. And now we can calculate again. So like in this case, maybe we should calculate the area of the whole object. So let's see. So the area after one iteration here is the area of the 0th iteration, and then so what we do, we divide this triangle in 4 triangles, but we keep only 3 of them. So it's 3/4 of this area, and then you see the area n equals 3/4 to n of the area of the first triangle, or the 0th triangle, and we see the areas of the whole thing are reduced, and then the remaining object has an area of 0. So what is with the scales here? Epsilon n. In this case we just halve the scales in every iteration. So from 1 we go to 1/2, and then So this is 1 over 2 to power n. So before we always had scales which were divided in 3 parts. Now we divide the scale in 2. And the number of objects to cover the whole thing, now we need here 3 of this object, so it goes with 3 to power of n. And then we can calculate now the fractal dimension of the Sierpinski gasket. So the fractal dimension, we do again the same analysis as before. So we have the number of objects we need to cover this. That's 3, and then we have to divide by the scale. It's 2 to n, and so we see here with the same arguments that we have here logarithm 3 divided by logarithm 2, and that's something like 1.58. So we get a fractal dimension which is larger than 1 but smaller than 2. So that's actually a thick curve, the remaining fractal that we obtain here. Right, and this now were examples of such perfect deterministic fractals where we always were doing precisely the same procedure and divided always the object perfectly into smaller objects, and then we have this perfect fractals where we have here well-defined fractal dimensions. And maybe when you now compare these two objects, these three fractals, the Koch curve, the Cantor set, and the Sierpinski gasket, so you see that we always created perfect self-similar objects, and actually we don't really need to follow this formula to calculate the fractal dimensions, because what we do, we always change the scale and then see how many objects we need to cover the thing in the new scale. Yeah? So we can define a self-similarity dimension for these kinds of objects. Let's do this. Self-similarity dimension. So assuming we have such a perfect fractal as we had shown here before, and let's say if we magnify or we reduce the scale by a factor b, yeah, and then we say if we magnified the old object now fits c times into a new object, and then we have introduced here 4 constants. This constant b, the scaling factor, and here the factor how often the old object fits into the new, and now you see I said I have taken here 2 versions. Either I magnify or I reduce the scale, because I can create the fractal in 2 ways. Either I take the old object and just make so and so many copies. In this case it would mean I magnify the scale here by a factor 3, and then see how many objects I need. So I need 4 copies. Or I could go in the other way. I say I reduce the scale, so that's how I did it here actually. So I said I reduce the scale, and then I see how often in the new scale, how many copies I have to put in. Yeah. So you can either construct a fractal that you just magnify the scale and make several copies, or that you subdivide the object and have smaller structure by smaller scales. Yeah? So, and then depending on what you do, you either magnify or reduce the scale. But independent how you do it, you have these two factors b and c, and then just by comparison, by all this formula that we had here, then we can define the fractal dimension of such a self-similar object as the logarithm of c divided by the logarithm of b. So we don't need then to make an limes going to small scales and so on and so forth. We can directly write down the self, and this is called the self-similar dimension. Now there is another aspect of the whole thing. I mean, these deterministic fractals are nice and well, but if you want to describe objects in nature, they're too perfect. I mean, so the coastline will never have this perfect shape and the symmetry, so that you always make the same kind of deformation at smaller scales. And so there is something, if you want to model more natural object, there's random fractals. So what's the random fractal? So if we now do a random fractal, we make something very similar as we had here, only that we now decide by, for example, let's take the Koch curve. It's more easy to explain this in an example. We take the Koch curve, so I divide my old line into 3 segments. So that was my old line, and I've divided it into 3 segments. Yeah. And in the Koch curve, I always take the middle segment, which gets the deformation. And now in a random fractal, I can take any of the 3 with the same probability to make the deformation. Then you see, I will always do this deformation. So this meaning the lengths, the scales, and the number of objects to cover this will always be the same. So the fractal dimension and everything will be the same, but the object will look very differently. So let's do this. For example, I start here with my line. Now, so the next iteration, I divide the line into 3 parts. And now I take randomly one of them, and maybe I choose the first one. And then the deformation comes into the first of the segments. So that would be the object in the first iteration. It has the same length as the Koch curve in the first iteration, but it looks different because the deformation is at the end of the whole thing. And now we go to the next iteration, so we divide everything into thirds, so we look at a smaller scale. And then we have our our 12 small intervals. And now we again we take randomly which of the 3 parts gets the deformation. For example, maybe here in this case we choose in the left part the middle segment. Now here we choose the last. Maybe here again the middle. And in the last interval we take the last one. Then we have an object like this. And now we divide again every part here into thirds, and so on and so forth, and do this again. And then you can imagine if we do this again and again, we obtain an object which is irregular, which will be a fractal, but it can be have a geometry which is a bit more random, arbitrary. So we actually, with this way, we can approximate an arbitrary coastline and not always obtain this perfect snowflake kind of shape of the Koch curve. And the same, of course, we can do with other things, like for example in the Cantor set, we divide the objects by 3, but we not always remove the middle part, but we could also remove the first or the second, first or third. Or in the Sierpinski gasket, we could remove either of the 4 triangles. And yeah, so when we do this, if you follow this up here, so we will now obtain a fractal which is a bit more naturally looking than the Koch curve. And so these random fractals make them very good models for example here for a coastline. Or if we have 2-dimensional fractals, it would be good models for example, mineral deposits and so on. Okay, so maybe with this the video gets too long, so I will stop at this point, and I want to thank you.